Hi and welcome to today's lecture on network media. This is Joe Johnson, instructor for cybersecurity and networking. And today's lecture is going to be about network media. This lecture is for the Guide for Networking Essentials, 8th edition, and we are on Chapter 4. So that's where you should be paying attention to. The objectives for this chapter are to define the primary cables used in wiring networking, describe the characteristics of the major types of fiber optic media, and explain the technology used for wireless networking. So this whole chapter is just about the physical and wireless connections between our computers and how we connect them together. Wired networking uses tangible physical media called cables. So when we talk about wired media, you're going to actually be able to see the media. Right? They're tangible, they're physical. Whereas in wireless networking, we can't see the radio waves that are sent back and forth from the access point to the stations. Today, we use two broad categories of cables. One is copper wire and one is fiber optic. And we're going to talk about the main differences between those two. Here's some key differences between copper wire and fiber optic. One is a composition of the singles. When we're using copper wire, we're going to send an electric pulse over the single. Over the media. We're going to send 5 volts or 0 volts, but it's going to be actual electricity that we send across the cable. When we use fiber optic, we're not going to use electricity. We're going to use light. So fiber optic is going to be more like a wireless networking, where you have energy in a waveform that is sent across the cable. One of the other big differences is the speed at which signals can be sent. Fiber optic cables have a lot higher throughput speed. The reason they do is because we don't have all kinds of interference. Fiber optic cables are immune from electromagnetic interference, so we can send signals at much higher speeds. That also affects the distance. So we can go over a lot further distance with fiber optic cable than we can with copper wire, just because of the noise immunity. We don't have signals from garage door openers and microwaves interfering with the wiring, or light ballast interfering with the signals on the wire. So when somebody asks you to go ahead and set up a new network, we're going to have to look at a couple of different criteria. And you're going to have to talk to your customer about it. It's not going to be something that you decide. I mean, you're going to make a recommendation based on what you know about the cabling, about the network media, but it's going to be based on your customer's needs. So the first thing we need to find out from the customer is how much bandwidth do they need. Are they just going to be transferring documents, or they're going to be doing full frame video across the network? We need to know that. And not only do we need to know what they're going to do today with it, we need to know in the future what they plan to do with it, so that we can prevent the network from becoming obsolete because they can't get the speeds that they want. Just remember, typically with higher speeds, you're going to pay more. So there's a cost benefit analysis you have to do. We also need to look at the encoding of the signals. Are we going to encrypt the data? How are we going to send the signals across the medium? When possible, choose a cabling category that's compatible with the standard you want to implement now, but will support growth at faster speeds. Like I said, you want to make it so that their network doesn't become obsolete because of future bandwidth needs. If that makes any sense. We also need to look at how far away the computers are from one another. Are we connecting a network that is in buildings across different sides of the city, or are we just connecting computers that are on different floors of the same building? So we need to look at the maximum segment length. There's going to be a distance that we can travel with a cable. For Ethernet, for fast Ethernet, that maximum distance is going to be 100 meters. And once we get to that length, we're going to lose our signal. So we want to make sure that all of the connecting devices or the computers are at least 100 meters, at most 100 meters apart. If we need something longer than that, we need to look at another option, such as coaxial cable or fiber. Each cable type can transport data only so far before its signals begin to weaken beyond what can be retrieved. When the signals weaken from traveling, it's called attenuation, and it happens with all media, or all signals. Even with fiber optic light, we have attenuation of the light. So what we're going to do is we're going to figure out what is the scope of the network. Is it going to go across floors in a building? Is it going to go across buildings? Is it going to go across the city? We need to find that out. And remember, we need to think about the future, not just right now. So maybe they might want to expand their network to another building later on. We need to look at the company's strategic plan. Strategic plan usually is, 5 years out or so, maybe even 10 years out, and see what they plan to do. If we're concerned about security and the performance of the network, if it's really performance sensitive, then we need to look at this EMI interference, and we also need to look at eavesdropping. Interference to electrical signals on copper media comes in the form of electromagnetic interference and radio frequency interference. So what happens is we have all of these magnetic fields out in the world, and when they impede on the media, what they do is they induce current on the media, and they mangle our signals. So what we want to do is, if we're in an environment that has high EMI or high RFI interference, such as an elevator shaft or a factory floor, we might want to switch to something like fiber that is more immune to this interference. Again, motors, transformers, fluorescent lights, and other devices out there create intense electrical activity, right? So we want to make sure that the environment that we're working in, the type of cabling, can work in there with all of the interference that is present. And then we also worry about that with wireless networks also. So RFI can affect wireless networks. When a signal impedes onto another cable, so maybe I lay two cables next to each other, and the magnetic field from one cable induces current on the other cable, that's called crosstalk. So what we do is, typically in a cable, if we have two wires running next to each other, we will twist them to cancel out the crosstalk. So crosstalk is when a signal from one wire jumps onto another wire. And that happens because of the magnetic fields that are generated by current going through the wires. Remember also that copper wire is susceptible to electronic eavesdropping. So I can put up an antenna next to your Ethernet cable and eavesdrop on the signals that are inside because of the magnetic fields that are created. Remember that fiber optic media carries light signals. It's not susceptible to RFI, EMI, or to eavesdropping. So fiber optic is very secure. It's also very dependable because we don't have magnetic fields interfering with the signals. The only really disadvantage to fiber optic is it's more expensive. We also want to look, when we buy the cable comes in different grades. We're going to look at the building codes. There's certain types of cabling that are created so that we can put it inside the walls and the ceiling of our building, and they won't create toxic fumes when they burn. Okay? Those types of cables are called plenum cables. So let's see, let me go ahead and highlight that for you because they talk about that some. All right. So plenum cables don't create those toxic fumes when they burn. Okay. We also have riser cable. Remember, riser cable has to do with going between floors. And then plenum. Right? So we see those markings on the outside of the cable. That tells us that the cable is rated for those purposes. Remember that CMR can only be used for building risers or in cable trays. And CMP is suitable for use in plenum spaces. Okay? So we see this word plenum. It means the spaces above the ceiling or below the floor. So the wiring that we're going to use inside of the structure of the building has special codes that you need to follow. You can't just put any type of cable in there. These types of cables are typically more expensive. But to pass inspection, when the inspector comes, you need to use these special ratings of cables. And then we also have to, when we look at the cost, we have to look at the cost of the connection hardware. Okay. So every type of cable has different connectors. We need to make sure the connectors in a computers match the connectors in the wall sockets. And then we need to make sure that the connectors on the switch match the wall sockets or the patch panel. So we need to look at the connectors. Connectors have a range of how much they cost, so you need to build that into your estimate. So when you're working for a customer and you say, I'm going to put this type of cable in there, don't forget to look at the cost of the connectors. Typically an Ethernet connector for RJ45 jack will cost like 10 cents a piece, whereas you might pay $5 for a fiber connector. So it can get pretty expensive for these connections, so you need to make sure that you figure that into the cost. Other factors to consider when you're choosing network media is how hard is it to install? Can we get people that are low skilled, maybe people that actually work at our company already, to do installations, or do I need to hire an outside company? Yeah. Some of the factors that you need to look at with cabling is there's always a rating called the maximum bend radius. It limits the angle which the cable can be bent around a corner. Anytime you bend a cable around a corner, it stretches the medium inside. So if it's copper, it'll stretch the copper. With fiber, it'll actually break the glass or plastic that's in the cable. So you can't bend it completely in half. It'll ruin the cable. So we need to look at that. We need to look in the building if we're going to have any kind of these corners that are really sharp, and how we're going to run the cabling. Remember, there's a cost and time needed to terminate the medium. Some terminators take a lot longer. If you're doing fiber, you actually have to take the glass or plastic wire, and you need to cut it at a certain angle, and you need to use sandpaper to smooth it out. There's a bunch of things you need to do. So it takes a lot longer to terminate a fiber optic cable than it does for a copper cable. The other thing is we need to be able to test the network that we put in. So we have cable meters. So we need to make sure that we have cable meters to test those, or if we need to buy some, we need to do that. It's real easy to make a mistake when you are putting together a cable. You might put the wire in the wrong slot inside the connector and it won't work, and there's no way for you to know that unless you test the cable, and people start having issues and problems on their computer, and they don't tend to think about the wires in the walls when they're trying to troubleshoot. So we want to make sure we can test those wires, make sure they're not too long and that they're terminated correctly. Remember, when we figure out the total cost, we need to figure out the actual cost of the cabling that we need to buy, a big spool of it, all the connectors, the termination panels, which are in the server room or the communications closet, the wall jacks, the termination tools, and the testing equipment. And finally, you have to give them an estimate how long it's going to take for you to do all of that stuff, because you have to pay man hours for that. The first type of cabling that we can choose from is called coaxial cabling. They call it coax for short. Once was a predominant form of networking cabling. When I started first working in '96, I was working on a network and we had coaxial cable for our network. It was really inexpensive and easy to install. They started to phase it out in the early 1990s. We typically don't use coax now. We use it when we make a connection to a cable modem from your cable provider. But typically in networking, that's the only place we see it. It's used primarily for connecting internet and TV now. All right. And even that's going away when they're coming in with fiber to premises. So what they're doing is they're trying to send fiber all the way to your house. And once they do that, we won't see this coaxial cable anymore. It was very inexpensive. The problem with coaxial cable is that if we use coaxial cable, if you remember from last chapter, we talked about topologies, is we're locked into a bus physical topology, and it forces us to continually take down the network to add stations to it. So that's one of the reasons the coax isn't as popular now as it was before, because we like physical stars now. Twisted pair cable became popular after the coax. Most of the coaxial cable got replaced with twisted pair. It comes in two flavors, unshielded and shielded. Shielded is for environments where you have a lot of interference, and shielded costs more. So shielded has a piece of foil that is wrapped around the cable to block out this interference. So it's more immune to interference, so you get faster speeds. Unshielded twisted pair is cheaper, but doesn't have that extra protection. Remember that twisted pair, the reason we call it twisted pair is we twist the wires inside of the cable. We have 4 pairs of wires typically, and we twist the wires, and it improves the resistance to crosstalk and interference from outside sources. So the reason it's called twisted pair is inside of your Ethernet cable, we're actually twisting the pairs of wires inside. Remember that the more twists per unit, per length, the better resistance. Also remember that when you twist a rope or you twist a wire, it gets shorter. So cabling with more twist is more expensive because you have to have more material to make the cable. More expensive twisted pair is twisted, more and less expensive right. So the more expensive, the higher the category, it's twisted more, and it's better than less expensive cable. It provides a better pathway for higher bandwidth. So the more twist I have, the faster my data moves. Here's a picture of shielded twisted pair. Let me get my pointer. Notice here I've got some kind of shielding around the wires. So what's going to happen is when a magnetic field hits this wire here, what's going to happen is the magnetic field is going to travel around the wire and up the bottom. Remember that electricity, waves, anything like that is going to travel the path of least resistance, and it's less resistant. You have less resistance traveling around the outside of this wire through the foil than jumping through the wire. So that's what it's going to look like in a shielded twisted pair. Our magnetic fields are going to be routed around the wire. In unshielded twisted pair, we don't have that extra layer of foil. So what's going to happen is the magnetic field is going to pass directly through the wire and cause more problems. So that's the big difference and why you're going to pay more for shielded twisted pair, because it takes more material to make the shielded twisted pair. Most networks use unshielded twisted pair. That's just because of the cost. Typically, the business people want to go with the cheapest option. Unshielded twisted pair consists of 4 pairs of insulated wires. 4 pairs means 8 wires, right? It's rated according to categories devised by the EIA-TIA and ANSI. So these are standards organizations. We have categories 1 through 6A and category 8 in the U.S. Other countries, we might have other categories that we use. But you'll see 1 through 6A and category 8. There's 2 addition categories that aren't standards yet. They may never be in the U.S. European Union has accepted category 7 and 7A. And inside of there, it's going to be more expensive because each wire pair is shielded also. So we have foil around the cable, but we also have foil around the pairs. Categories 5E, E stands for enhanced, and 6 are the most installed categories of unshielded twisted pair. Okay, so we have a table on the following slide. Shows us these characteristics. So for a twisted pair cable, the maximum cable length is going to be 100 meters. So you can go up to 100 meters with a run of twisted pair cable. If it's any longer than that, the cable may work, but it's not going to be dependable. All right. We want to follow these standards. If we don't follow standards, then there's no guarantee anything will work. So maximum cable length is going to be 100 meters. The bandwidth is going to be up to gigabit Ethernet. The bend radius is going to be 4 times the cable diameter, or 1 inch. And we have tools to measure the bend radius. Installation and maintenance. It's easy to install, no need to reroute, and it's the most flexible. Because it's a star topology with twisted pair, each computer is going to have its own run of cable. It's the least expensive of all the cabling options. The connectors we buy are RJ45. It's moderately susceptible to eavesdropping. Like I said, I can put an antenna up in the room and monitor what's going across the cable. The signaling rates depends on the category. 100 megahertz, that's 100 million cycles per second for category 5E, or 250 megahertz for category 6. Remember, it is susceptible to this EMI and crosstalk. So it is cheap, but we have less features. Shielded twisted pair cable includes shielding around the cable to reduce the crosstalk and interference. It's got typically has a wire braid inside, or a foil wrap. The wire braid is usually grounded at the ends to pull away interference. It's best to use shielded twisted pair in noisy environments or with very high bandwidth applications. Remember, the more shielded it is, the higher bandwidth you get, and we want to use it in places where we have motors and things of that nature. Shielded twisted pair has a category 5E, category 6, or category 6A, and sometimes they call it FTP or foiled twisted pair. So this is a picture of a shielded twisted pair. Remember, it's going to be more expensive because it is foil that's made into the cable. We also have this cord right here that's used. A lot of people use it for stripping the cable. Typically, it gives the cable strength. It's usually made out of like Kevlar or something. And then we usually have a mesh with this wire through the wire. And what we're going to do is at the ends of the cable, we're going to ground that to pull interference away. Because we have all this extra stuff inside of the cable, it's going to be more expensive. When we install twisted pair, remember we're going to have to buy connectors. The connectors we're going to have to buy, the standard is called RJ, Registered Jack 45. RJ45 connectors are most commonly used in patch cables. So a patch cable goes from your computer to the wall. Definitions here, patch cable. It connects the computer to an RJ45 wall jack or to a patch panel to a hub or switch. So patch cable is not really in the wall. A patch cable is something that an end user or a technician can access and switch to different ports or plugs. So a patch cable is actually a cable that you'd be able to see. It's not in the ceiling or the walls. Remember, RJ45 jack is what you plug the connector into. So RJ45 jack is a female. It's basically a hole in the wall. And then you take the RJ45 connector and you will plug it into the R45 jack. This is a picture of an RJ45 plug. So we've got a couple of things going on. Right here, you'll see there's some metal inside of this connector. And what's going to happen is you're going to take your cable and push it into this end. And then I'm going to have a special tool called a crimping tool that's going to push these metal teeth into the wire so that it bites the wire. Once you do that, you can't pull the wire out anymore, and it makes an electrical connection to the wire. This little tab at the top is going to keep it from falling out of the wall jack. To get this connector out of the wall jack, you're going to have to push your thumb or your finger on this tab and pull it back out to get it out of the wall. We talked about a patch cable. This is a patch cable. Notice we have twisted pair. This is what twisted pair wiring looks like. It's got connectors on the ends. So we see these plastic connectors that we looked at on this last slide. You can see the wires that are inside the connector. They're different colors. This is probably a pre-made cable because of these plastic connectors that are over. These things protect the connector. It stops this tab from getting caught in other wires. So this is probably a pre-made cable. They're not made by the end users. And notice on our Ethernet cable, we also have the category stamped on it. So if we were to read this from the information that we already know from the chapter, we would say it's a category 6 cable. Do you remember what UTP is? It's unshielded twisted pair. Notice we also have some stuff you really can't see it, but it says TIA EIA. That is going to be the standard. So it's going to have a number there to tell you exactly what type of rating the cable is, how fast we can send data over it. This looks kind of funny. You've probably never seen this before. This is what the jack looks like inside of the wall. So this is inside the wall behind your little plastic cover that looks like kind of a light socket cover. All you're going to see in the outside is this hole. On the back end of this, inside of the wall, you're going to have wires pushed into these slots. These slots have metal connectors in there, and when you push the wire down, it bites into them and holds them. So a technician is going to come with a special tool called a punch down tool and push the wires into these slots inside of the wall. We're also going to use things called patch panels. Patch panels are used to terminate long runs of cables and wiring closets. So let's see if I can find a picture of a patch panel. There we go. So inside of our communications closet, we're going to have a piece of metal that has all of these RJ45 jacks in it. So this one might come from a patch panel in room 1. And this one might come from a wall jack in room 2. And this one might come from a wall jack in room 3. So all of the cabling that comes from the different parts of the building come into this one patch panel. This is the back of it. And I'm going to push the wires into these slots with a punch down tool. And then I'm going to use a patch panel to connect this port to a switch that's in the server room or the communications closet. Inside of the communications closet, we're going to have racks, and the racks are just metal poles that hold equipment. So we're going to have these metal railings that we are going to take a bolt and mount this patch panel to the frame of the distribution rack or the rack. A lot of people call them server racks, but all they are metal poles, and we bolt devices into them so that this won't move once we have it set up. Here's what a rack would look like. Remember, it's just a metal pole. And then I take a patch panel and I bolt it into there. I can bolt my switches into the rack. I can also mount routers and servers into the rack. And this is going to be inside of your communications closet. You're not going to see this out on the public area where users can see it. So when we are putting our cable into the building, maybe we have a new building, maybe we have an old building, we're going to have to follow certain rules when we put the cabling in. The rules that we have to follow are called the structured cabling rules or standards. These are the standards that the inspector is going to use when he looks at the building. Just all kinds of rules about where we can run cables and where we can't. One of the things we don't want happening is we don't want to have our power distribution wires, our Molex, our wires that carry voltage next to networking cabling. The fear is that if you put them in the same wire tray or conduit, that the 120 volts or 110 volts is going to jump from the power system to the networking equipment. So we have all kinds of rules about where we can run this cabling. And if you run it in the wrong place, then the inspector is going to come by and he's not going to allow you to let people in the building because it's not done correctly. So these are the areas that are going to be structured cabling areas. So we're going to mark all our areas with one of these categories. And we're going to have work areas. Typically in work areas, that's where people are going to be. We're going to have horizontal wiring. That's wiring that goes along the floor or along the ceiling on the same floor. We're going to have telecommunication closets. That's where wiring comes together. We're going to have equipment rooms where we have servers and routers and switches. We also have vertical wiring. That is wiring that goes between floors. Typically, that's going to be a backbone, or they also call it risers. Risers go between floors. And entrance facilities. Don't be fooled. Entrance facilities are not where your customers come into the building. That is where the cable company or your internet service provider is going to have their connection coming in and connects with your local LAN. So remember, work area is where the workstations and other devices are located. You have wall jacks in there, and we use patch cables. So work area is where the general public or the employees are going to be. Remember that horizontal wiring runs from the work area's wall jack to the closet. According to the specification, the patch cable should be no longer than 10 meters. And then the wiring inside the ceiling and walls, the horizontal wiring, should be no longer than 90 meters. If you add those together, you get 100 meters, which is the maximum run for Ethernet. So this is what you would see in the work area. You would see the computer. You would see a patch cable. Remember, patch cable maximum length is 10 meters, plugged into a wall plate with an R45 jack. Typically on every floor, we're going to have a telecommunications closet. So all the wiring, all the horizontal wiring from the different offices is all going to come together in this telecom closet. Inside of there, we're going to have connectivity devices such as hubs and switches. The telecom closet that houses the cabling and devices for the work area computers is referred to as an intermediate distribution frame, an IDF. So people are going to throw around all these terms when you get inspected and stuff like that. They're going to talk about IDF, and it's better if you know what they are when the inspector comes and people start talking about it. So here is the work area here. So the work area ends at this wall jack. This horizontal cabling goes from the back of the wall plate across the ceiling or the floor and all the way to the intermediate distribution frame, which is going to be on the same floor as the work area. We also have equipment rooms. In the equipment room, we're going to have servers, routers, switches, and other major networking equipment. It serves as a connection point for the backbone cabling or the risers or the vertical wiring, as they call it. So we're going to have a room with all our servers and all of our equipment in there. It's going to be called a main distribution frame, and all of the intermediate distribution frames are going to feed into it. A main distribution frame can be the main cross-connect for an entire network, or might serve as a connecting point for another backbone between buildings. Each building's probably going to have its own main distribution frame or server room. So you'll hear people call MDFs server rooms because that's where all of our equipment is. Backbone cabling interconnects intermediate distribution frames and main distribution frames. Cabling runs between floors or wings of a building or between buildings. We typically use something that can travel long distances. So this backbone cabling is typically fiber optic because of the distance, and also because we need a bigger pipe to connect those smaller pipes. So the data that's flowing into our intermediate distribution frames is going to give us a certain amount of traffic, and since we're adding all that traffic together, we need a bigger pipe. So typically we're going to use fiber optic cable that can handle more bandwidth. An entrance facility is a location of the cabling equipment that connects a corporate network to a third-party telecommunications provider. So the example would be your ISP. So your entrance facility can be your main distribution frame. It could be the same thing. It all depends on where the cable company or the telephone company brings their wires into your building. One of the important terms you need to know is the demarc point or the demarcation point. It's where your responsibility ends. So when you're thinking about the demarcation point, think about your cable at home. What are you responsible for with your cable? Are you responsible to climb up the telephone post and change settings on the wire on the telephone post? Typically not. That is maintained by the cable company. If there's a break in the telephone, in the cable at the street on the pole, they fix that. They are typically responsible for all the wiring all the way up to the box that's on the outside of your house. It's typically a box on the outside of the house, and it might be buried or it may come in from a telephone pole. But everything on the other side of the box belongs to you. So if you have a problem with one of your coaxial cables inside of your house, then that's your responsibility. You have to pay to fix it. The reason why it's so important is we also look at equipment with demarcation points, and we might have some kind of expensive switch. And if the switch goes bad, we need to know whether it's the cable company's responsibility to fix that, or if it's our corporate responsibility, our corporation's responsibility to fix it. So that demarcation point needs to be clear. So this is what we were talking about. We've got intermediate distribution frames. So this would be, let me get my pointer. This would be the distribution rack. This would be the equipment closet on the first floor. This would be the equipment closet on the second floor, our intermediate distribution frame. And then we're going to have, orange typically means fiber. So we're going to have a backbone cable, typically fiber, that runs from these equipment closets to the main distribution frame, where we're going to have all of our servers. So we're putting all of these terms together and showing you how they relate to one another. When I'm installing unshielded twisted pair, when I use the term termination, that means I'm putting one of those plastic connectors on the ends of the cable, or I'm punching down some wires into the patch panel or the jack on the wall. We need specialized equipment to do that. We need a roll of cable. We need wire cutters. We need cable strippers. We need a tool that pushes those wires or conductors into the teeth in the connector. We need a type 110 punch down tool to punch the wires into the wall jacks. We need a cable tester so that we can test the cable and make sure it's up to specifications. And then we also need all of the connectors, the RJ45 connectors, and then the jacks, and we need a patch panel. Remember? So use this chapter when you're making an estimate to remember everything that you're going to need to buy. You don't want to give the customer an estimate and then lose money because you forgot to add something into the estimate. Here's a picture of many of the tools that we're going to need for working with cables. Let me get my laser pointer. This is a crimping tool. What would happen is you take the plastic connector and put it in that hole right here, and then you squeeze it. And again, that's going to make those teeth bite into the cable. And then the cable won't come out anymore. Right? So this is for terminating the wire. This punch down tool is for terminating the wire inside of the wall. So when we come to the jack in the wall or the patch panel, we're going to use this to push the wires into those white connectors. Electrician scissors is what we're going to use to cut the cable. We can always use cutting pliers also. This cable stripper takes the outside jacket off of the cable. And then finally, after we've used all of these tools, we're going to use a cable tester to make sure that our connection is sound inside of the wire, and we're not going to have any further problems from the wire after we install it. When making a cable or terminating a cable, it's important to get the color wires arranged in the correct order. There are two different standards for the coloring. We have the TIA-EIA, remember that's a standards organization, 568A and 568B. Whatever you use, you just need to make sure that you stick with it. If you don't use the standardized wiring colors, then the person that comes behind you is going to have problems because they assume that you're following standards. Always follow standards. So here is, let me get the little laser pointer again. Here is our connector for RJ45. It's a plastic connector that we buy. Notice there's 8 little slots or places for a cable to go, a wire to go. And what color we put in these little slots when we're making the cable depends on which wiring standard we're using. If we're using 568A, we're going to use green, white, green, orange, white, blue, blue, white, orange, brown, white, brown. If we're going to use standard B, we're going to start out with orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. Whichever standard that you use on one end of the cable, you need to use it on the other end of the cable if you're making a straight through cable. So if you're making a normal cable that connects devices, unlike devices, then you're going to use the same standard on both ends of the cable, either A or B. We also have another type of cabling called another type of wire called a crossover wire, a crossover cable. We're going to use 2 different standards on the ends of the cables. So if we want to do a crossover cable, we use 568 on one end, we use 568B on the other end. Crossover cables are special use cables. We use them when we connect like devices. So if I need to connect a computer to a computer or a router to a router, then I'm going to use a crossover cable. You cannot use a straight through cable to connect 2 computers directly to one another. The NIC light won't come on and you won't be able to send data over those cables. So this is a crossover cable. Notice I have one standard on one end, starting with white, orange. On the other end of the cable, I start with green, white, green stripe with white. And again, that's called a crossover cable. And you use crossover cables to connect devices that are the same. On our switches, typically we're going to have a newer feature called MDI. MDI stands for Medium Dependent Interface, and what it's going to do is it's going to adjust our device to match whatever type of cable we put in it. So if we take 2 switches and we connect them together, typically we're going to have a crossover cable, but if you have this nice feature inside of your switch called MDI, what's going to happen is the switch is going to recognize that you're using the wrong type of cable and automatically make adjustments, and the cable will work. So know that a nice feature that you can get for your switch is this feature called MDI that will automatically adjust to the type of cable in case you don't have the right type of cable. But typically your device, you should assume that your devices are not going to have this feature. So you need to use the right type of cabling for the situation you're in. So we've got 4 pairs. We only use 2 of them. And the question is, why do we have 2 transmit and 2 receives? What we want to do is be able to use a pair for transmit and one for receive so that we can have full duplex communication between the devices. So I can transmit in both directions at the same time. I can send a packet from the switch to the computer and send a packet from the computer to the switch at the same time. Okay. All right. We also need to talk about fiber optic cable. You won't see fiber optic cable as much. With fiber optic cable, the bits are transmitted as pulses of light instead of electricity. Remember that it's going to be immune to any kind of interference on the cable. Remember that fiber optic is highly secure because you can't eavesdrop on the wire. You would actually have to tap the wire to eavesdrop on it, and people are going to know if you tap their fiber optic cable. Inside of a fiber optic cable, we have a cylinder of glass or plastic called the core. It's surrounded by another layer of glass called the cladding. The cladding is going to reflect the light back into the cable because the light's not going to travel in a straight line. Remember, light travels as a wave. So we're going to use the more dense cladding to reflect the signal back into the cable so it doesn't get lost. The fiber is then jacketed. That means they have outside, they're going to have PVC or some kind of plastic material called the buffer. And then they're going to have something on the outside to protect it from the elements. Typically, we're going to have more than one strand in a cable. So here's our picture. We're going to have our glass called the core. We're going to have our inner jacket, which protects it and also reflects the signal back into the optical fiber. We're going to have Kevlar inside of the cable, and that gives it strength so that we cannot pull the cable and break the glass inside of the cable. So if we didn't have this Kevlar in there, we could stretch the cable and it would fracture the glass inside of the cable. And then we're going to have a protective jacket on the outside, and that just keeps the water out. Remember, we typically use fiber optic cable as backbone. We typically have 12 or more fiber strands inside of the cable. Even if we are using only 2 in the backbone cables, running more is a good idea so that you're ready for future expansion. So the big expense for fiber optic is going to be burying the line or running the line. So what you want to do is, if you got some money to buy a cable with more runs inside of the cable, you want to do that, and that'll future-proof your network. It's been shown that glass fibers can carry several terabits, 1,000 gigabits of traffic per second. So here's a summary. We've got different types of fiber optic cable, so the maximum cable length for it is going to be 2 kilometers to 100 kilometers. So I can run a cable 62 miles with fiber. Do you remember what the maximum length for the copper cable is? It's going to be 100 meters. So a lot longer distance. The bandwidth is going to be 10, 40, or 100 gigabits or higher. so really high bandwidth. The bend radius is going to be 30 degrees per foot. Remember, we have devices to measure that bend radius. Remember that it's difficult to install and reroute, and it's sensitive to people bending it and pulling it. Once we put it in and it works, we don't usually want to mess with it. It's the most expensive of all cabling options. The connector types, we have several types depending on how far you're going with the cable length. It's not susceptible to eavesdropping, and it doesn't have any interference in line. So that's why our singles can go these long distances. We have many different types of connectors. We have a straight tip connector, a straight connection, a SC, a locked-in connector, a LC. So we have all these different options, and it all depends on what your equipment has at the ends. Typically, we're not going to plug these fiber optic cables into a computer. They're going to be plugged into telecom equipment. Notice they all look different. And again, it's all going to depend on the manufacturer of your switch or your networking equipment. I've seen one similar to this on digital audio cables also. So you would plug this into the back of your stereo, maybe back to your high definition TV, and it would carry an audio connection. It's a lot more expensive to pay somebody to install the fiber optic network than it is to pay them to do copper. We are getting more pieces of equipment that make it easier, so the cost is coming down. Remember that all of the connectors and the testing equipment, the meters, are still more expensive than copper. We have a lot of different connectors. And then if I'm going to install fiber, you're probably going to have to do a little bit of training. The copper wire, typically somebody can figure out. You don't have to be an expert on it. Fiber optics a little more sensitive. So if you buy a kit from the store, you're going to have a buffer tube stripper and cable stripper, a crimper, a diamond cleaver, an inspection scope, and a polishing tool. And it doesn't look like they have pictures of those devices. Different options we have is single mode fiber and multi-mode fiber. Remember, single mode fiber is going to have a single strand in it. Because it is a single strand, it's going to go further distances, and it's going to be used in higher bandwidth applications. Okay. You're going to have a strong transmitter or emitter, and typically, from what I've heard, you need to keep this single mode fiber cables pretty straight, and you'll get that high speeds. The multi-mode fibers has a large diameter fiber at the core, and it's going to bounce more. So the light is going to bounce more in the cable. It's going to be cheaper than the single mode fiber, and it's going to work with the lower power, less expensive LED lights. So we're not using a laser at the end, we're going to use a LED. We can't go as far with the multi-mode fiber because, like I said, there's more bounce in there, and we use the lower power LEDs. So when I'm doing fiber, I'm going to have a cable certifier, a cable tester, a tone generator that's going to generate light into the cable, a time domain reflectometer that's going to measure how much reflection we have in the cable. If there's a break in the cable or we don't cut it correctly at the right angle, the light is going to be reflected back to the source, and we don't want that. So we use this TDR to check our splices. We're going to need a multimeter and an optical power meter. So it measures light, right? Optical is light. As people use the internet more and data and information more, wireless equipment, the demand for it has become increased, right? And the production of it has become increased also because we need it more. Always remember, manufacturing, the more of something you create, the cheaper it is, right? You save when you buy in bulk. So since we have more people creating networking equipment, it's going to bring the prices down. We're also going to use wireless networking. So like I said, wireless networking equipment has become more prevalent. It's getting cheaper and cheaper and cheaper. Wireless networks are used with groups of mobile users. So when we don't know where the users are going to be, we want the users to be able to walk around, then we're going to use wireless networks. Some of the cool things you can do with a wireless network that you can't do with a wired network is create temporary connections for your visitors. You can make backup or contingency connectivity. So maybe if there's a cable cut, we can use a satellite dish to send a wireless signal to the other building when our backbone is cut. Extend the network span beyond the reach of wire-based or fiber optic, where you might have older buildings. Maybe you're working in a historical building. Maybe it's an older home and you want to put internet in there because you're starting a bed and breakfast. Well, there's certain rules about what you can do and what you can't with historical buildings. So there's going to be maybe you can't change the look of something, or you can't get into the walls of the building, then we're going to use wireless. And remember, it's going to allow users to roam around the organization with their devices. They like being able to walk with their phones and doing work outside. Some other things that we can do with wireless networks is give access network to isolated facilities, or maybe if we're in a disaster area, we can bring in a mobile wireless truck that will give everybody access to a wireless network, so that first responders will be able to communicate with each other even when telephones are down. In areas where layout and settings change constantly, wireless is good. Think of a restaurant where you have customers coming in and out. So they'll be able to sit in McDonald's or Bojangles and be able to use wireless and not have to find wall jacks and plug into the wall. Some types of wireless networks we can have a LAN. That would be like the wireless network inside of your house. We have extended LANs, used to increase the LAN span upon normal distance limitations. So we might use it to have a network between buildings. Maybe I have a river running between the buildings I want to connect. What I can do is set up a wireless network that goes over a microwave link from building to building. We also use wireless networks for internet service. So you can have even the city that installs wireless in the downtown area and gives free access to wireless from its citizens. So we can bring internet service to places where people aren't able to plug in or access. They can still access the internet. And then for people with laptops and devices that move around a lot, you can have mobile computing networks. Most of the components in wireless LANs behave like the wired LANs. The network interface on your computer or device is going to attach to an antenna and an emitter or a radio rather than to a cable. So we're not going to have a wire that runs out of our laptop. We're going to have an antenna. An access point or a transceiver is a device that is installed to give us access to the internet from our wireless. So we need to have a network interface inside of our device that we want to use the internet on. We also need to have an access point that gives us access to the internet. Wireless communications depends on sending and receiving wireless signals broadcast through the air. So the signals that we're going to use are electromagnetic signals. Remember, it's going to take the form of a wave, and we're going to express we're going to talk about the characteristic of the wave in hertz or cycles per second. The lower hertz or the lower frequency carry less data, and the higher frequency carries more data. Remember, higher frequency, because it requires more energy, covers less distance. The lower frequency uses less energy, so you can carry data over longer distances. So there's a trade-off. Here are some of the common frequencies for wireless. If you're listening to the radio in your car, that's going to be 10 kilohertz to 300 megahertz. Microwave inside of your house is going to send out waves from 300 megahertz. Not microwave. We're talking about a microwave network, not the microwave in your house. The microwave in your house does send out these waves, but the ones we have standardized for communicating is going to be 300 megahertz to 300 gigahertz. And then infrared is light. We use those networks also. It's going to be 300 gigahertz to 400 terahertz. You don't need to memorize that. That's just giving you some examples. There's 4 primary technologies for wireless. We typically use the radio, but we can also set up wireless LANs to use infrared, like the remote control to your TV. We can also send signals with a laser. We can have narrowband, where we have a single frequency. That would be like your radio in your car. We can also use spread spectrum radio, where we frequency hop. Infrared wireless networks use infrared light. Infrared light is not visible to people, and it's going to send information back and forth between devices. It doesn't work well outdoors because we have interference from ultraviolet light and the sun. Also, you need to have line of sight, so that the devices need to be able to see each other with nothing in between them. So we typically don't see these infrared networks in use that much. Laser-based uses lasers. Remember that you need a line of sight between the sender and receiver, nothing in between, so it's not good for places where you have a lot of particles in the air or people walking in between the devices. The laser-based devices aren't as susceptible to interference than the infrared devices. We have narrowband radio LAN technologies. It's going to use low power two-way communication. It's going to be in one frequency. The problem is, since it uses a single frequency, it's real easy to have interference to block your transmission. Because it cannot change frequencies, if something creates interference, the narrowband radio is not going to be able to work around the interference. Whereas a broadband radio is going to be able to switch to another frequency and get away from the interference, the narrowband is not. So here's our narrowband. We have some bands that are frequencies that are not regulated. Those are the ones we're going to use. The maximum distance is going to be 70 meters. So not even as far as an Ethernet cable. The bandwidth is going to be 10 megabits per second. That's probably not going to be fast enough for your customers. It's easy to install and maintain. The interference is really high because we are going to be on a single frequency, and that's why it's going to be highly susceptible to interference. We can't work around it. And because it's wireless, it's highly susceptible to eavesdropping. Spread spectrum LAN technologies uses multiple frequencies. So if we do have that interferences at a certain frequency, we can work around it. There's two kinds of spread spectrum communications. We have frequency hopping. It switches the data between multiple frequencies at regular intervals. That cuts through the interference. And then we have direct sequence modulation. It breaks the data into fixed size segments called chips and transmits the data on several different frequencies at the same time. So instead of jumping to different frequencies at different times, it's going to use all the frequencies at the same time and use them like lanes of a highway. So we're going to get faster speeds with that. So the bandwidth is going to be 1 to 2 megabits for frequency hopping, 2 to 6 megabits for direct sequence spread spectrum. This is what you're going to see when you do Bluetooth. It's resistant to interference because, remember, it can work around the channel that has the interference on there. And it's not very susceptible to eavesdropping because we're using encoding, and we're also jumping to different frequencies at different times. So the eavesdropper would have to switch to those frequencies at the same time we were on them to eavesdrop. So, to kind of recap what we've been talking about, there's three main choices when we're selecting our media. If bandwidth is the most expensive to us, or the most important to us, then we're going to need probably fiber. So remember, these different interests are competing. The bandwidth works against the budget. So the higher the bandwidth, the more it's going to cost. If you're more budget conscious, then the bandwidth's going to come down. So they have like an inverse relationship. Unshielded twisted pair installation costs $100 to $200 per cable run. That's for the labor and the materials. And then fiber optic might cost twice as much. So you're paying twice as much for fiber. Then we have environmental considerations. How noisy is the environment? How important is your data security? Right? The more noisy your environment and the more data security is important to you, then you're going to pick fiber. Right? So budget and interference and security is working against your budget also. Okay. We also need to make sure that we work it into the existing cabling if we're doing an upgrade to an existing place. So we need to consider the existing cable that's in the company, and then we're going to talk about the distance, right? The span. How long do we need the distance to cover? Longer distances means fiber optic. So use this table right here when you're making your decisions about the case projects. When you're trying to select the right type of media, use this table right here. They're going to tell you we need this speed at this length, and we care about it's going to be high interference, and we care about security. So you just use this table to figure it out. You want to do the cheapest option you can that meets the requirements of what they want. Remember, you need to ask them about future requirements also. And that's the end of the chapter. So for this chapter, we need to know about copper cables, different flavors of copper cables. We need to know about fiber optic cables. And then we need to know about wireless. We need to know about connectors. and structure cabling rules. That's the big topics in this chapter. If you have any questions about the chapter, email your instructor and they'll get back to you pretty quickly. I guess until next week, read the chapter and do the activities. All right. Have a great week.